por el camino del desierto, el viento me despeina, suave aroma de colita, nada del aire.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. I'm going to finish off the chapter about resonance by talking about resonance contributor preference rules. So now that I've shown you how to actually draw the resonance structures, now that you've drawn 2, 3, or 4 different structures for a particular molecule, how do you know which is the most likely, or which is going to be the biggest contributor out of the 3 or the 4 that you drew? Well, there's 6 rules that I'm going to go over, and rule number 1 is the more influential than all of the other preference rules. And then rules 2 to 6 have no particular order of preference. I'm just going to list them in the order that I wrote them out. So let's start with rule number 1. Rule number 1 says that the most important contributor has the least number of avoidable open valence shells. So I'll abbreviate that to least number of avoidable valence shells. So as an example, let's draw this molecule. We have CH2 and then double bonded to OH. And there's a positive formal charge on this oxygen, which you can figure out if you calculate the formal charge using the equation that I showed you before. And then the resonance structure for this would look like this, where you have CH2 plus with a positive charge on the carbon, because this is now a single bond, and you have 2 lone pairs on the oxygen. So basically, we push this onto the oxygen. So in this case, if you look, all valence shells are filled. Because carbon has 1, 2, 3, 4, meaning 8 electrons, oxygen has 2, 3, 4, 5, 6, 7, 8, and hydrogen is happy as well. In this case, you have an open valence shell on the carbon, because carbon only has 2, 4, 6 electrons, so basically it's lacking 2 electrons. So in some cases, it may not be possible for all the atoms to have full valence shells, which is why we come up with rules 2 to 6 as well. But in the case that in one scenario all valence shells are filled, and in the other there's an open valence shell for one of the atoms, this guy is always going to be the preferred resonance structure. So this guy is preferred. And I'll give him a star. There we go. So now let's move on to rule number 2. Rule number 2 says that the most significant contributor has the maximum number of covalent bonds. So I'll write that out as max number covalent bonds. So as an example, let me draw out this molecule. We have CH2, double bond O, draw out the lone pairs, and then its resonance structure would look like this. Oops, my lone pairs are looking weird now. Okay, so as you can see, this double bond was broken. There was an arrow that pushed another lone pair onto the oxygen, and now it has a negative charge. So in this case, we have 4 covalent bonds, right? 1, 2, 3, 4. And in this case, we have 3 covalent bonds. 1, 2, 3. And so in this case, this is going to be the preferred resonance contributor. Again, we'll give him a star. But as you can see, even by following rule number 1, which says the least number of avoidable valence shells, comparing these two, carbon has a full valence shell right here, whereas it does not right here because it has 1, 2, 3 bonds. So actually this carbon should have a positive charge right there. So now moving on to rule number 3. Rule number 3 says the most significant contributor has the least number of avoidable formal charges. So least number of avoidable. Again, we keep using this term avoidable because in some cases it is not avoidable, in which case you have to check out some of the other rules. So in this case, the example is this guy, the same as before. And if we get the next guy, which I just showed you above, so I guess I didn't have to draw it out, but here you go. Now we have a formal charge on the carbon and the oxygen, right? We have a +1 here and a -1 here. You can calculate it yourself for practice if you want to. So in this case, we have no formal charge, and in this case, we have a +1 and a -1. Thus, this is going to be the resonance contributor that is preferred. So now I'll move on to rules 4 to 6. So moving on to rule number 4. Rule number 4 says if a contributor has unavoidable formal charges, the most important contributors have these charges on the atom or atoms that can best accommodate them. So in rule number 3, we said the most significant contributor has the least number of avoidable formal charges, right? But in the case that you can't avoid the formal charges, we have to figure out which one is the lesser of the evils. So let's see. When you have a negative formal charge, it's best on atoms of high electronegativity. So for example, you would prefer to have an O- versus a C-. If you have a positive formal charge, you actually want this on atoms with low electronegativity. So in that case, you would prefer C+ versus O+. In another case, you also want to minimize the formal charge magnitude, meaning the +1 is better than +2, which is also better than +3, etc. For example, if I had CH3, double bond O, and then CH2, and this carbon has a lone pair and thus has a -1 charge, and this has a resonance structure where we again still have the methyl group, but then we have a single bond to the oxygen, and now we have a double bond to the carbon to make CH2. In this case, carbon has a negative charge for this structure. In this case, oxygen has the negative charge in this structure. So as we talked about before, for a negative formal charge, you want it on the high electronegative atom. So in this case, this structure is preferable because the oxygen has this -1 charge versus this carbon having a -1 charge. So this guy is preferred. So now moving on to rule number 5, we're almost there. Resonance interaction, i.e. pi bonds, is the strongest between atoms in the same row of the periodic table. So resonance interactions, i.e. a pi bond, is strongest between atoms in the same row of the periodic table. So usually this is carbon, nitrogen, oxygen, and fluorine, which are in the same row of the periodic table. And this usually outweighs electronegativity considerations. So rule number 4. So rule number 5 is usually overruling rule number 4. So as an example, if I drew out carbon double bonded to fluorine. So now this fluorine has a positive 1 charge, and we have chlorine and a hydrogen right here. And then we draw its resonance structure, which is fluorine with its valence shell, carbon, hydrogen, and then chlorine. So both these structures look kind of weird, but let's look at the first one. Fluorine and carbon are both second row elements, and the more important contributor, even though the electronegativity of fluorine is greater than the electronegativity of chlorine. So remember before we said for the positive formal charge we want it on the low electronegative element, which is chlorine. So initially you would think that this is the preferable structure. But as I said, rule number 5 overrules rule number 4. So think of this as rule number 5 bigger than rule number 4. So in this case, since carbon and fluorine are in the same row, that overrules the fact that chlorine is less electronegative. Carbon is in the second row, but chlorine is in the third row, and thus this is the less important contributor, and this guy is preferred. Finally, rule number 6, which I'm going to draw right here because there's not much to say, is that there's other factors, which I'm not going to talk about just yet, such as aromaticity, that we will encounter later in upcoming chapters. So just keep that in mind and stay excited for more exciting topics that are upcoming. And so violations to the resonance contributor preference rules exist, but they're uncommon. So basically when you're drawing your resonance structures and trying to figure out which is the more preferred resonance contributor, you can often follow rules 1 to 6 that I wrote out right here in the order of preference that I noted, which was rule number 1 is the most important, and rule number 2 to 6 are all about the same, but rule number 5 overrules rule number 4.